Hi guys, welcome to Learn Electronics Repair. I have an amplifier here to repair today. This thing, so JBL MPX600, okay. The fault, according to the guy who brought me this one in, is translated from Spanish as one channel collapsed. So probably one dead channel. Maybe just how the translation came. So this video may be as much an exploration of the fault as a repair. This may need some parts. Because he says we have one dead channel, I'm going to open this up first and have a look inside it, rather than just plugging it in, even with the current limiter. Let's see if we can spot anything obvious, and also just get an idea of what architecture or topology this amplifier has. Although I expect from the weight of it, this is a Class AB amplifier. I will mention there's quite a bit of corrosion on this thing, by the way, which is making it a bit difficult to get some of these screws out. Very difficult, in fact. Oh yeah, I mean those are really seized. We can see here, this is quite an old thing made in the USA. I say it's quite old because it has these kind of like terminal posts. It doesn't have the speak-on connectors on, so it must be of a fair age, I think. Not sure I actually see a year code on this, but I'm guessing it's over 20 years old. Still trying to get into this. I've put a bit of like WD-40 type similar stuff on here. Actually no, I think this is marking multi-purpose oil. Just trying to get the corrosion out of the screw heads to see if I can actually get the screwdriver to go in them properly. Otherwise it's just going to strip the heads. I'll end up drilling these out, I think. But let's see. Can I get it or not? The screwdriver's a good fit. No, man. Well guys, I got into it in the end. These things are still seized into here. I just did it by sheer brute force. Basically, if I tried to drill the heads, it wouldn't go. So I effectively like deformed the metal a bit, so you know, just came over the head. I'll figure out how to put it together. Probably if I can get these out, it shouldn't be too much of a problem. Put some new ones in. So we can see inside this now. First thing we notice, a very large laminated core transformer. So this is pre-toroidal transformer, which makes me think this thing is probably considerably older than I expected. Great, this could be back from the 80s, I really don't know. I was building amplifiers with toroidal transformers in the early 80s for our own mobile disco, so yeah, maybe it is newer than that. Little vertical boards in here. It doesn't have the old TO3 style transistor, so actually I'm guessing it's a bit newer than that. Okay, so it's very dusty and dirty, that's the first thing we can say. Okay, so that has the worst of the dust out of it at least. We can see 4 fuses here, 4 more fuses here. There's the fuse down at the back there as well. This is where the power comes in, so that might just be on the mains, that fuse. I only see one of them. Okay. Quite a number of wires coming from the transformer, so 5 of them here, 5 more of them here. Probably some of these are in parallel, but I see 4 fuses, so okay. Another 4 here. Let's just check the fuses first. Well, that one seems to have blown. And that one, oh no, that one's okay. This one looks okay, but don't seem to find any continuity. That one's okay. That one's okay. That's okay. That's okay. Yeah, they all seem okay apart from this one, but it doesn't look like it's... Yeah, it's okay, look. Just a bad connection against it. Okay. Take this one out, but it's okay, it's just... doesn't seem to have a very good connection for some reason. Even that isn't even easy to get out. Well, it looks okay. But I can't read across there. I can read across there. It must be okay. Yep. Well, I can read across it now. Okay. So let's look at the main fuse. I'm assuming if one channel's working, this must be okay. Yeah, as you'd expect. Just try the ones on this side. Okay, 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 okay. So my first thoughts are, if the fuses are all okay, there aren't any shorts. Yeah, these are the bridge rectifiers, by the way, these big things. I just noticed 4 legs on each. Yeah. So there aren't any shorts. That's the first thing I would say. So in that instance, I'm going to power this up with a current limiting light bulb in. Let's see what it does. I also notice, as well as having the 4 and 4 fuses, we have 2 bridge rectifiers here, we have 2 bridge rectifiers here, so 4 bridge rectifiers in this. That's a little bit unusual, but hey, that's what we have. Yeah, I can see the output transistors down there and probably driver transistors. I also see, if I show you guys, in this row here, there's a diode there, and there's actually another one just here. So we have pairs of transistors and pairs of diodes there and there, and I see the same arrangement in this other block over here. So you see the pairs of diodes, pairs of transistors. Now that suggests we have a class G amplifier which has switching power rails, so a high voltage and low voltage plus, high voltage and low voltage minus. Quite why we have the 2, I don't know. It's kind of like these are almost 2 separate power supplies, one for each channel. There's some symmetry here, like 2 of these little boards, 2 rows of 4. But then we only have a pair of these coils, a pair of these relays, which I guess are the protection relays. It is only a 2-channel amplifier, by the way, it's not a 4-channel. Okay, well, that's what I can see at the moment. The fact all these fuses are okay suggests to me there isn't a short in the output stage. So let's connect our power lead with the current limiter. Let's see what this does if we try to power it up. So there's the light bulb. I have it set to limit. What happens? Well, bright then dim. I have a clip light on one of the amplifiers, so it's not going to blow up. It's drawing a fair bit of power, but these things usually do with these big transformers in them. Let's just get a camera on the front panel so you can see what it's doing. Yeah, you can see it from that angle. So it's now switched to direct mains. This is on. Let's switch this on and let's see what it does. Okay, so we see one channel is going into power and the other one is stuck in protect. Okay, so that's what's wrong with it. We have one channel running, and the one that's in protect also says there's a signal present as well. Yeah, show you that again. So, okay, it's powered off now. So we have power and protect for the two channels, and then we have clip and signal for each channel. Okay, so this left hand channel protect goes off, it goes to power, no signal, no clip. Okay, this one stays in protect, and we have signal and clip. Okay, I've also just I'll show you guys. These are the little vertical modules, those modules there, just behind this cable, and I have the same on the other side, kind of behind the transformer, so I'll have to do that. Hope it doesn't make you feel seasick. Okay, so what's happening is, this one on the side that shows the protector, you see there's two red LEDs lit up on that thing. Okay, and the other side, sorry about this guy's yellow, they're not lit up. Okay, so we see some red LEDs on there as well. I also see an LED lit up red here dimly, and another one here which isn't lit up. So that's basically what I have. Looking at these connectors, this one with the 4 wires, you can see that goes down there, and that goes to the speaker connectors. I can see where that goes. So this is your right and left output. Okay, then I'm guessing this is power for this amplifier, this is power for this amplifier, and then we have another one down here which may well be 15 volts. So I think what we best do is have a look at the voltage around these bridge rectifiers on both sides, just to try and get some idea of what we're looking at here. So you can see the bridge rectifiers. Okay, the other side you can probably see some markings of these. Actually, no, I don't. Trying to figure out which is the AC, which is the DC on these. Well, normally you'd think the middle two are probably AC. I doubt the capacitors are holding any charge because the thing's obviously powering up and then they discharge. But what we can probably say is that the fuses are almost certainly connected to the transformer, so the AC. Yeah, and they'll all just read short because they're all on the AC, on the windings. So we can say this is AC. They're not really short, I'm just reading back through the windings in the transformer, okay? So does that go to the middle pins on these bridge rectifiers? It looks like it. I'm having a bit of trouble getting a good connection because of the corrosion, but it looks that way. And they don't go to the outer ones. Okay. Oh, it goes to that one though. Hang on, is this a capacitor charging somewhere? That's interesting. Goes there, and now there's a capacitor charging. Just give it a moment. Could be a capacitor charge in the opposite direction. Yeah, see it go there. So it's not a short. So the outer legs are the supply rails, I would say, and they're not connected to each other in parallel. No. So I think if we can measure from ground to the outer end of each of these, we'll probably find a plus and minus applying the same on this side, I'm guessing. So let's see if that's what we actually do have. I'm hoping this is actually ground. It'll probably be short for me via the transformer winding if it is. No, maybe that isn't ground. Where do I find the ground on this thing? The reason I thought it did really short from the fuse is because the ground would be the centre tap, basically. No. Well, that leads to the metalwork of the fuse, and this looks like it's probably a ground to me, that one. So let's say that this is ground. Okay. Let's check from here with the voltmeter there. So power up. Let's look. So we have plus 48. Other end. Minus 48, the other one. Plus 97, minus 97. So this is class G. Oh! That reads 140. That reads minus 3. 85. There's something very strange about the voltage readings on this side, the one with the red lights on. Can you see that? Quite what it is, I'm just trying to figure out, but there's something very strange on this side. So, looking at the good one, plus 48, minus 48. Okay, and on this one, plus 193, and almost ground. Interesting. Very interesting. And the other one, again, this was the higher voltage, plus 96. Try even get a reading on this one. Minus 96. 144. 48. I think something's getting a bit warm here as well. Maybe the thermal camera will tell us something. So, okay, two things. One, we need to see if we can find the schematic. And B, let's have a look around. Oh. Hold on a second. Down there. That. Oh, and that. Yeah. They look bad. These are probably the emitter resistors. So 1, 2, 3, 4, 5, 6 devices. 1, 2, 3, 4, 5, 6 devices. And it looks like, yeah, 1, 2, 3. Oh, this one's gone as well, I think. And it looks like 1, 2, 3, 4, 5, 6 there. And yeah, 6 resistors. Okay, so if these are the emitter resistors, which I think they are, that probably suggests there is a short in these output devices. But the reason it hasn't blown the fuse is because it's blown these resistors. Let me just draw that, give you an idea. And I think the reason I'm seeing like double the voltage as expected is something to do with I'm seeing across the two rails reading from positive to negative and not to ground effectively. It's a guess. So we're going to have, assuming the polarities could be different, but in the output stage we're going to have probably an NPN device. These are those emitter resistors, and obviously there's 3 of these in parallel. And then the other emitter resistor, and then a PMP, yeah, like that. And this is your out, but there's a relay on here, so we have the relay contacts here which then goes to your speaker, okay? And the other end of here is ground, yeah, because it's not in bridge mode. But you can put it in bridge mode, by the way. So we have that. This will go to the plus HT, and this will go to the minus HT, okay? And then the HT is switchable, so this isn't a fixed voltage. This will have basically a diode coming in like this, which is HT low plus, and then it will have a transistor or MOSFET in here, okay, and this is HT high plus, okay, and the same on this end. So on this end you'll have a diode like so, and this is going to be HT low minus, and then again another transistor in here, PNP in this case, okay, and actually probably the other way will probably be the emitter to here, but anyway, and this will be HT low, sorry, high minus, okay. And what I think we've got is shorts in here and or in here, and instead of blowing the fuse, it's blowing these resistors, okay. And that's what I think we have, and I think we've seen some kind of like weird readings on the supply voltages, which can't be twice as they should be, because we haven't got a proper reference to ground on the multimeter on the bad channel. Something like that, but let's see, because you're going to have to figure it out, okay. So the capacitor should be discharged by now after I was showing you that. These emitter resistors are going to be low value. Go to resistance range, they'll be very low. Yeah, 0.9, they're probably 0.2 actual fact. This meter doesn't zero very well. Okay, this side. Same. 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 And I'm guessing on this one that they're open. There's a guess, just a guess. So, yeah, these mega ohms, yeah. And these will effectively be in parallel, well, each one going to a set transistor, which are also in parallel. Yes, so they've all blown. And then these are okay. If one reads okay, I'm sure they'll all read okay. Yeah, they read okay. Yeah, and that one. So those all read okay, and these read bad. So one set will go to the transistor onto the negative rail, one on the positive. The top and bottom of all this is we need to get the PCB out, and let's look for a schematic as well, which I mentioned before. Yeah. Do we have one? Oh, looks like we might have. Oh, Electro-Tanya. This is a really good site, this is, guys. You can find a lot of schematics on here, you know, and I've never ever ended up with some virus or malware. As a non-member, you can download 10 schematics a day. I'm actually a member on here, but like from 10 years ago or more. And I honestly don't know what my login is. Unless you've changed it with this site, you have to pass an online test before they allow you to join, because they don't want people who don't know what they're doing messing around with stuff, yeah. So, seriously. Hey, I'm in, look how about that. So, go to download. I've heard, or Det tells me, that AI can now solve those puzzles, by the way. So hopefully the horrible things will go away because they'll be useless, yeah. Oh, well, that's just one page. So you can see your output devices here, 3 and 3. Look, here's that circuit I told you about. Diode from the low tension, MOSFET from the high tension. So this is switching the positive voltage. Again, diode pointing the opposite way, you'll see here, because it's negative. Yeah, look, there's the diode. And again, the same thing with the MOSFET, switching the negative voltages. And basically, we're seeing some very strange voltages around the negative side. I've just found another document on the Electro Tanya, so maybe this is not the same. This one says MPX300, MPX600. Okay, comes as a raw file this time. Oh, this one has more. Yep, chassis. That certainly looks like the one I have. So a bit more information on this one at least. I'm guessing now that those funny little modules we can see are actually these things. That's why we don't see a schematic for that part. So this actually really is a schematic, basically. Or close to being one. Yeah, here's the input and everything. That's definitely our board. And the connection diagram. Okay, so we have some information here. We know then we have switching MOSFETs and we have bipolar transistors. Bear in mind this schematic is for one channel, so we effectively have two of this lot. We can see some of the port numbers. Looks like it's a bit blurred, but yeah. Q503 maybe. Q504 maybe. That's the MOSFET that switches the voltage rails. D502, D501. So we can sort of see the main components. I'm going to be looking for faults around these MOSFETs, around these diodes, and around these output devices, considering we have these burnt out resistors. Also notice that heatsink ground is where I was actually measuring my voltages to, and in the case of these resistors being open circuit, I may not have a proper voltage reference when I'm trying to measure these output voltages. But that's why I think the 100 volt rail was looking more like 200 on the positive and more like 0 on the negative. Okay, let's see what we've got on our board. So here are the output devices, 6 on this channel, 6 on this channel. We can see 2 diodes. Those are probably that 501, 502. Yeah, D501, 502. The diodes in this type of circuit are always big ones, guys, so they probably mount it to a heatsink like this. Yeah, we have 4 transistors here now. Those 2 are obviously bipolar. These could be the MOSFETs, which are switching voltage. Yeah, D601, 602. Yeah, and then some transistors. These could be MOSFETs. So we want to look at 2 places. First of all, because we have these strange voltage readings, let's have a look around these diodes and MOSFETs. And then because we have the burnt out resistors, which we can clearly see here, let's look around the output devices on both channels and see how they compare. Diodes first then. This is the channel with the burnt out resistors. Okay. The other channel comes out of protected, probably okay. So, one here. That reads like a diode. And the other way around, I see a capacitor charging, okay. The other diode, that is probably a capacitor charging actually. Let's see if it keeps going up. No, that's a diode. And the other way around. When we go from a minus into a positive, this is a capacitor charging up, I would say. Yeah, it keeps on climbing. Let's compare that with the good channel. Or we're pretty sure it's good. So, that reads like a diode. The other one read like a diode in the same direction. Do we see capacitors charging this way? Yeah. Yeah. Let's look at the output devices. So we have one here, 1, 2, 3, another one, the third one, the fourth one, the fifth one, And then the 6th one just goes under the edge of there, and the same over here. Let's go to the good channel to see what we'd expect. So I'm going to say, basically, we're going to get 3 NPN and 3 PNP transistors. So the first one, this would be the base. So we'll put the black on the base. That reads like a diode junction if this is a PNP. And this you'd expect it to read quite low, because there will be a low value base emitter resistor. That said 70. It's probably 22 ohms or something. Yeah, 22 ohms. How about that? I'm so familiar with my multimeter in diode mode. Okay. So this the same. And then low. And then from the collector to emitter, we'd read open. Reads open. Well, it's a high value. It's just going up. Capacitor charging somewhere, I think. This one, diode, reads low. Okay. So these are PNP. It looks like PNP. So if we go the opposite way, with red to the base, yeah, there's no diode there. So on the PNP, you'd expect the collector to be a lower voltage than the emitter. So that's why we should see high or open in this direction. In the opposite direction, so with the collector positive, that's like the reverse polarity to how this would work in the circuit. We might see a diode. And that'll be on all of them because they're in parallel. Okay. Okay. So these ones, the other 3, well, we don't see a diode now with the black to the base because these are going to be NPN. So that actually, no, it doesn't read short. It was a capacitor charging. You see what happened? And to the emitter, low value. Next one, diode, low value. Diode, yeah, low value. And then in this case, with the negative to the collector, because that's the opposite polarity, we might see a diode like we did with the other ones, yeah, on all of them. And with the positive to collector, which is a normal operating polarity, it should read basically open. That one reads open. Yeah, that reads open or high. Same. Same. So PNP near the middle, then NPN. Let's look at the other ones. So the first PNP is kind of tucked under here. If it is PNP, they could be the same way around as those. Base collector. That is short. Base emitter is short. Collector emitters are short. And we'll see that on all of them. And the reason being they're in parallel. So it could be that only one of them is short, but we see the short everywhere. And without a milliam or micro ohm meter, you can't really say which. But with these devices, if one has failed, I tend to change all of them anyway. Let's go to the other block. So we got 1, 2, 3. This is also reads short. Reads short. Yeah, they are all short, both the NPN and PNP. So we need to take those out. And after we've taken those out, we need to look around this lot and compare with that lot. But there's no point in doing that until we take these out, because the short will easily give us the wrong reading and confuse us, okay? So desolder that lot. And we can see the devices now. So 2SC3281 and 2SA1302. I also believe I can explain those strange readings now. I was saying that it's because I thought that where I was connecting to ground isn't really ground anymore, yeah, due to a fault. Now, if we look at this, I'm measuring with my meter probe here, okay, and these 3 resistors here are all open circuit, so there's no connection there, okay. This one may well be open circuit as well. I haven't had a look. But assuming this is open circuit, and this is reverse biased, we can see. And on the negative side of the amplifier, these, although the transistors are short, these resistors are intact. So in actual fact, I mean, ground is ground. This is the same place as here. So when I put my black lead on here, and I read to the negative supply rail, well, it's shorted via the transistors. So from here to here, we'll read 0. And that's what I saw on the negative rail. And when I put my black meter probe here, and I measure to here, well, the black probe basically is now at minus 100. And the red lead's at plus 100. So I will read 200 from here to here. Okay, so I hope that explained that. I hope you followed that, because I thought that was quite interesting. It also suggests that this could be open circuit depending where A goes to. There could be an open circuit there as well. I'm sure we will find out, because we can check that. I've started to remove the transistors. You see it says CCC, AAA. So these are the 2SC transistors. These are the 2SA transistors. You may remember now, but you'll probably forget by the time the replacements turn up. Yeah, so just to save any confusion, and you don't want that sort of confusion, I will tell you. I've unsoldered the first one with the vacuum desoldering tool. You can probably hear it in the background. But I'm going to try using the hot tweezers plus a soldering iron. I've not done this before. Let's see how well this works. It's easier to remove the solder after you've removed the components, if you can do that. In fact, it's fairly easy with braid once you've removed the components. But it seems like a perfect chance to try this thing again. So 350C. I'm not sure how well this will work, because you really need 3 hands, but I've pushed the long nose pliers into the hole on the heatsink of the transistor. I'm literally going to try this. Does it work? Probably need some leaded solder, but I had to put some leaded solder on when I used the vacuum tool anyway, so no difference really. Let's see. Of course, I should do this with the big soldering iron really, but I can't be bothered to put this one down and pick the other one up. I'll then decide that it would have been quicker if I'd just done it in the first place. Of course. Just do it in the first place. Let's have a go. So we'll add some leaded solder. I'll do them all since I'm here. The other technique I use with just a soldering iron is to warm each of the 3 pins up very rapidly and just pull the thing out while the solder is still molten. So 2, 3, 4, 5, this is number 6. Right. Let's see what happens. So it fell out of the board. Yeah, you see that? It just fell out. And that in that one. Yeah, this one didn't fall out. That maybe that was a fluke. Yeah. Yeah, that one fell out as well. I wouldn't say this method's any particularly quicker. Let's try that with just a soldering iron. This way, just stick this into the hole. and it's a matter of trying to get all three to melt at the same time. You see it's coming at one end. This is working, but this is harder. I think this board has some quite heavy tracks on it, so it takes quite a bit of heat. No, that's not easy. We can use this technique just to see. That's fairly easy. So having tried this a few different ways, I've put this up to 400 now rather than 350. This may actually be the easiest method. Yeah. How about that? Let's see how many of these transistors are actually short. Well, that one is. Yeah, and that one. And they're all completely short, so they're short to the base as well, which would suggest that some high voltage went into the base and therefore into whatever is driving these. Oh, that one, interestingly, reads okay, but I wouldn't trust these. I'd just replace all of them. Okay, so we have two that are okay-ish, and four that are bad. 2SA, 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 and then one of the 2SCs. Okay, the 2SA are the PMP, so they're on the negative side, so that explains why those resistors exploded. And these two read okay. Now let's look at these components. These may be drivers. I'm just looking to see where they're connected in the circuit. I know two of them are the diodes on each side. What do we actually have here anyway? Let's see. So MJE15033 and 15032. You would expect these to be a complementary, one NPN and one PMP. They are bipolar because they're marked base collector emitter. There's one of the diodes, SF82, and another one the same. And then these are MOSFETs, okay, Q503, Q504, and Q501 and 502 for that matter. So 501 and 502, the bipolar transistors, these are the drivers for the output. I would expect these to be damaged on the blown channel. I would be tempted to change them even if they're not, to be honest. And look at these resistors around here, 517, 518, okay. Also that one, 543, I think it might be. And if these are damaged, we should go further back. So we have a couple of diodes in here, which is part of the bias circuit. there's bias adjustment. Then basically the drive comes from this op amp over here by the loops of it. And the other, well, there's 504 and there's 503. So those are the MOSFETs that switch the positive and negative voltage rails. So we know exactly what we have here. And then the large diodes, again, are part of that switching circuit. One of them is there and one of them is there. Both the MOSFETs are the same type, so they're both the same polarity, yeah. And we can see that from the schematic anyway. Right, let's look at the driver transistors. So base collector emitter, one's NPN, one is PNP, and this is the good channel. Well, that reads open, that reads open. This could well be the PNP, so we'll put the black lead onto the base. That reads a junction, that reads a junction. So this is the PNP, this is the NPN, so the red lead on the base. They read okay. This is the good channel. So the NPN, you would expect the collector in normal operation to be more positive than the emitter. So this should read open or a high reading. Okay. And the opposite for the PNP, so the emitter would have the higher voltage than the collector. And that reads a high reading. If you read them the other way around, you may see a diode junction depending on what else in the circuit. Yeah. See, that's in the opposite polarity to how it operates. As is that. Okay, so we know how they read. Let's look at the other ones on the bad channel. So this one, black to the base, junction, junction, and then the other one, red to the base, junction, junction. So it reads okay. This will be the NPN, so collector positive, should be like a high reading. In fact, without the output device in, I'm just seeing open. But bear in mind I have some open circuit resistors on this, okay? And the other way around, I may well see a diode junction like I did on the other side. But I might not, because the other transistors are not fitted now, okay? And I don't, but bear in mind those are not fitted. And this one, with the emitter positive to the collector, reads high. The other way, like you read a diode junction on the other channel, this does read a diode junction. Interesting, that does. That doesn't, so I'm going to check the diodes around here as well, okay? So the transistors read okay, but I have a slightly odd reading. Let's look at the diodes. So we have one of them here. That reads okay. And basically it's just climbing up, probably a capacitor charging. This one, it doesn't read short, that's the capacitors. Does it stop at the, yeah, the voltage of the junction, 0.453. This should just go upwards. Again, have a capacitor charging somewhere. Going through 0, up the other way. And this will keep climbing. And then we'll look at the other side to see. Okay, yeah, look, it's continued to climb up. Diodes on this side. Well, that reads like a diode. Does this show the capacitor thing? Yeah. This one reads like a diode. And we see the capacitor thing. Okay. Let's look at the MOSFETs. I may have to take these MOSFETs out to test them, to be honest. So they're both the same. This will be gate drain source or gate source drain, depending on the pin out. So from the gate to the source and the drain should basically read open. Well, that actually just gives it a reading, not a junction. That reads like a junction. This is the good channel. That reads like a junction. That doesn't. Well, that's interesting because they're both the same device. Yeah. And we know this channel is working. Others. That's short. That one is short. Yeah, that has a similar reading to one of these. But no, not the same. Yeah, it has a reading like that one. Okay. So it looks like I have one short and one okay, but I'm going to unsolder both of these and let's have a look. These are fairly easy to desolder with just the soldering iron because the pins are much closer together. Okay. Short. And it was short on all pins, yeah? So that includes the gate. This one is a good one. But since I need to replace the other one, I'll replace this as well. Anyway, it may have been stressed. What else may be wrong with this? I'll take these two out and test them as well, just to be sure. If they are okay, then probably everything further back is okay. On the amplifier, this is the amplifier effectively, yeah? This is the audio path. The switching for these MOSFETs goes via a resistor straight into the module. So these are modules on the board. There's one on the positive, one on the negative. So there's two per amplifier channel, okay? If the module has been damaged due to the failure of the MOSFET because it is short to the gate, then this is a problem because I don't believe we can get these modules anymore. And I'm not sure whether we can repair them. Depends if we can actually identify the components on. So let's check now. I think the best way to test this is going to be to measure the resistance from the gate to ground and also to the positive and negative supply rails. Because you can see here, this module, let's see, it has gate power is coming in this case from the -53. Okay, that is just goes down to the -100. Okay, and then this on the plus, okay, +100, +53. So let's measure from the gate to the voltage rails on the good and the bad channel, and let's see if it's the same or if we see a difference. You can see these are 63 volt capacitors and there's 4 of them on each channel, okay? And the high voltage rail is 100 and the capacitor is lower rated than that. So we're going to say for sure, and we'll just check this, but I'm sure we will find that the junction of these two is ground. That's the -50, the -100, and this is the +50 and the +100, okay? So if that's the case, let's just check. And we should know, I do know, and we all should know, that the capacitors must be wired like that because of the 100 volts. Yeah, the 63 volt capacitor. So I'm thinking, if I can find it. Well, that's interesting because it don't seem to be wired the way I thought they would be. That also looks a bit suspicious. The solder joints here looks a bit suspicious to me. Could be a dry joint. It's not obvious that it is, but I'm going to fix that one here. Something like that in the amplifier could easily be what caused this to blow up. Yeah. Well, they look a lot better now anyway. And there's another one. Doesn't look quite so suspicious, to be quite honest, but I'll resolder it. I'm just trying to figure out how these capacitors are connected up now. So they're not in a row. You can see that these four are all wired off down this way. This is the bad channel. These are the MOSFETs that switch the voltage rails, okay? These bad joints are on that channel, but that could be caused by the failure. Hard to say, really, unless we investigate, which we will do. And then these four appear to be on this channel. They all kind of come this way. So we have minus plus, minus plus. Yeah, like that, minus plus, minus plus, that's how they are. This is a good channel. So we can see straight away the positive of this one goes to the negative of that one. The positive of this one goes to the negative of that one. So the positive of this one goes to the negative of that one. So they're in series, yeah, you can see that. This is the negative end of the high voltage. This is the low voltage. And the same the other side, low voltage and then high voltage. Yeah. Let's look at the bad one. So we should have the same sort of arrangement. So that's the polarities. Same as the other side. That goes to there. And this goes to here. I can see that much. Positive of this goes to the negative of that one. And then positive of this one goes to the negative of that one. Yeah, and positive of this goes to the negative of that one. So they're just arranged differently, okay? Right. Let's look at the resistance from the gates. So the good channel, which is on this block, yeah, what have we got? 4.8 meg, 6.4 meg, 6.5 meg, 3.8. So they all read high. Into the mega ohms. Other one. All read high into the mega ohms. Now let's look at this channel. So gate would be here. Mega ohms. Mega ohms. And the other one. Well, they all read into mega ohms. I'm not saying they all read the same, but they all read into mega ohms. So I don't think we've got like a short in the driver module. You know, that's kind of like best I can say. If we do have a faulty driver module, well, it seems to consist just of transistors, resistors. I don't see any chips on there, and I don't think there's anything on the other side. They flushed against each other, so I would think these things are repairable if needs be. I think if we could identify the SMD devices, they are repairable. Okay, so low value resistors. These have clearly failed. We know these are bad. Okay, they read open compared to on the other channel. They read low, and they should be low. 0.22 ohms, yeah, very standard value. So I need to replace all those. I read 0.8, but my meter doesn't really zero very well on low resistors, but these things don't like really fail apart from when that happens, so I'm not worried about that. Let's have a look at the other power resistors as well while we're here. Should check them. So this looks like a 2.7 times 0.1, 2.7 ohm. Yeah, read something down towards that. 2.2 and 0, so 22 ohm. These will be the base resistors, I would think, for the output devices. 22 ohm. 22 ohm. That one, no, 22 ohm. This is fairly typical, so if these are 0.22, these will be 22. Okay. This one, another one, same as that. 0.27, 2.7. Yeah, close. This one, I think is orange gold. Yeah, so this probably 3.3. Reach close enough to that. This one, yeah, same. These are the ones in the drive to these, I would say. Okay, or to the MOSFETs. Okay, a lot of corrosion in this. You can see it's very dirty. Possible one of these has failed. The bias adjustment. That can also cause this to go bang. Down here, another one, 3.0 and 2 more zeros, 3K. Yeah, it reads close to that. This one, 22K. You see how important it is to learn the resistor color code? Because think if every time I had to go on the internet and look it up or look at the printout, it's going to take a lot more time, yeah? So they look okay. There's a whole bunch of them here, and I think 2 of these is where those dry joints were. Okay. Or possible dry joints. So this one, 4K. Huh. What value is that thing supposed to be? Can't easily see. What do the ones read? About the same. About that. Another one. About the same. That one reads much lower than all the other ones. That's the 680 ohm. Okay, so 680 ohm reads a bit lower than that. Yeah, look, 3.9K, 3.9K. 3.9K. This reads 4K, so I'd say it's a 3.9K. And then a lower one. Yeah, 1, 2, 3, 4 at 3.9 and a lower one. So we should find the same on this, which will be for the other channel. Here. 3.9. 3.9. Yeah, same. Same. And there's the low value one. Yep, 680 ohm. So that looks basically the same. What else should we test here? Well, the short would have drawn a lot of current through the bridge rectifier, so we should test these. Diode mode. This is the positive. I think this is the positive end of the bridge. There's a plus there. So let's have a look. So this is the positive end. Put the black lead on, red lead to the two center ones. Diode. Diode. Okay. And then this will be the negative end, so this should be opposite way around. Diode. Diode, and then the same with the other one. So one bridge rectifier for the plus and minus high voltage, the one for the plus and minus low. Well, it's still 50, yeah. So that reads okay. That reads okay. That reads okay. So it hasn't damaged those by the looks of it. I think probably now just a final check. I'm a bit concerned about that thing. I have one on the other side. Okay. But to change these, you would have to adjust them. Yeah, and I'm not sure how to adjust these. I don't have a service manual. I have a schematic. I can have a look to see if the resistance looks the same to the wiper as the other channel. Yeah, but it may not be the same because of the bias adjustments. And I probably need to adjust these anyway by replacing the output transistors. So that reads 16 ohms that way. This reads almost 0. Other one, which I'm pretty sure will be this. They say bias by them, so we know it's the same thing. This one, about 0, about 17. Okay, I'm happy enough that they're okay. I'm not going to mess. And for completion, let's just look at all the diodes in this channel, yeah, just to see if they look like diodes on my meter. Looks like a diode, Zener diode actually. If it reads like that, 0.7, it's probably a Zener. This could be a Zener as well. Yeah, Zeners read a bit higher. You see that, guys? This one, yeah, looks like a Zener down in this area, but I don't think any damage has come this far back. Diode, diode. I'm not going to mess around with the little transistors down here. As I say, it looks like the damage didn't get as far back as this. Okay, little bridge rectifier here, but I'm not seeing any problems in this area, so I'm quite happy really. Yeah, I think that's all okay. I'm not sure if I tested that one. What is that thing? It's a bit hard to read. It looks like it's been getting rather hot. What does it read? Ohms range. $5K. Unfortunately, the markings have kind of come off. I have the schematic, of course. It almost looks like this is a yellow, which makes it into the hundreds of K, but it can still be less than circuit. You can see one on the other side that looks like that. Well, that's our 637. And here's 537, so I'm assuming it's the same as that one, because there is some symmetry on this. So that reads 2.9K. Looks like it's a 3K in actual fact. And this one, a bit more. I'll find it on the schematic. Let's have a look. Well, looking at the schematic, 537 is a 3K. And that's what it reads. Now, there's nothing on here which is 6 whatever. So I'm taking the basic assumption, I think it's a good one, that the number started from 6 as the other channel of the amplifier. So same number, but with a 6. Look, like you see, it's showing them like effectively like equivalents here. So it must be 537 and 637. So this connects from the 53 volt rail and it goes to an LED. So this is just driving an LED. And the equivalent on this side, which is, wow, it's so bad you can't read the markings on it, but this would drive the equivalent LED on the other channel, and it reads 5K, so the LED would still light but probably a bit dimmer, but we may as well change that at the same time. I don't have any 3K, but I have some 3.3, and hey, it's only lighting an LED, yeah, so it ain't critical. So let's unsolder some resistors. This is where the resistors blew up. We see a bit of damage to the PCB here, so we should have a look at that. Yeah, this area of the PCB has no copper, so I'm not too worried about that. Yeah, in fact it just burned into the PCB a little bit, like where the resistor was, okay. But it's only a double-sided board and there's no copper there, so I'm not concerned about that. Okay. I will just add that it's quite evident that whoever designed this thing wasn't really thinking about efficiency. Using high-powered resistors to light LEDs, for example. Yeah. Efficiency was not the main concern here. You could say, well, look, it's a 600 watt amplifier, so, you know, what's 10 watts here or there doesn't make any difference, but, well, comment, guys, about that. I think it's a bit unusual to find so many high-powered resistors in an amplifier circuit like this. I think probably if we get all the replacement parts, which we know are faulty, this will be good. Let's have a quick look at the Hall of Infamy, or Shame, yeah, the Hall of Shame. So here are the remnants of our 0.22 ohm resistors. I have these in stock, slightly different shape. Oh, tell a lie, I do have some of these, but I don't have many, so I may as well order some more of those just to keep the stock level up a bit, yeah. Very common resistor and amplifiers, those things. This one I showed you 2 watt. I have a 3.3, but I think you can now see this like it was a orange originally. So I'll put a 3.3 in, that's fine. These things I can find on AliExpress, 10 for €4.15 with free shipping, or 5 for $3.39. Yeah, may as well have the 10, I guess. Hopefully I can trust them. And these things, well, these I can get on AliExpress. I had a look, so 5 pairs of each is €8.79 with free shipping. There's a number of companies selling poles, and I'm just starting to wonder, are the poles more likely to be original? But then, you know, what did they come out of? Are they stressed in any way? What would you guys do? Would you go with some new ones? Would you, you know, just get like a load of poles and just test them yourself? They're roughly the same price, to be honest. All black. Black and green. Okay. Yeah, he says they're all dismantled. I mean, you would assume that they're going to be original. That's the first thing you can say. And if we test them on the components analyzer and they're okay, they're probably okay. Discuss it, guys. But yeah, I can get them. As I said at the start then, this is not going to be a completed repair because I knew I would need parts. This is basically what I need. Those are my good ones, so that's basically what I need. Some of these do read okay, but I'll change all of them, to be honest, including the one that doesn't read like it's faulty. Yeah, I think we found a pretty good explanation of what caused the fault on this. because those solder joints around these resistors look bad, and this is all part of effectively the driver circuit that balances this amplifier, so I'm sure that sort of failure would cause that to blow up. So I think we have a pretty good cause of the fault, and I think if we replace everything that I've tested, this will probably work. I've done the best I can to test the gate drive from these modules. Obviously I can't completely, but resistances look in the same ballpark at least. Yeah, and I probably can't do any much more than this other than fitting the parts now and trying it. What I will do in the meantime is have another good look around this amplifier for any more suspect dry joints. At a glance, it kind of looks much more okay than what I found here. Yeah, but I'll have a look around it. And of course, if you guys have spotted something, I'm sure you're going to let me know down in the comments. Hope you enjoyed that. There's another good demonstration of how to fault find these amplifiers, and I'm sure you'll see this again because we need to put the parts in, put it back together and see if it works. So for that and for other videos, I look forward to seeing you all soon again on Learning Electronics Repair. Ciao for now, guys.